Fixed routing rules age badly as prompts and prices change. A Vowpal Wabbit Contextual Bandit learns which model meets quality at the lowest cost from logged outcomes. You'll build a Contextual Bandit LLM router with epsilon-greedy exploration that selects the lowest cost model passing the quality gate and reports IPS-adjusted cost. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Routing LLM calls is a daily ops headache. Teams pick a model and never revisit it. That wastes money on easy prompts and risks failures on the hard ones. A Contextual Bandit adapts routing from live telemetry, so cost and quality balance themselves over time. Vowpal Wabbit fits nicely. It handles logged bandit feedback and lets you update online without rebuilding a batch model. Here's the workflow. For each prompt, we send features to the bandit. It returns a probability distribution over models. We sample one, run the LLM, check a quality gate, and log that single outcome back. Over many interactions, the router learns which model tends to be cheap and good for each prompt shape. We'll implement a tiny live loop that queries Vowpal Wabbit for a route, logs the chosen action and its probability, converts pass-fail into a cost, and updates VW online. That gives you a decisioner plus a monitoring signal that corrects for exploration bias. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We start with the smallest live router that returns probabilities instead of rules. This snippet creates the smallest Vowpal Wabbit Contextual Bandit router and asks it for an initial route. It uses the -cb explore flag with epsilon, so VW-predict returns a probability mass function over the 3 entries named mini, base, and pro. At the start, the model has no feedback, so the PMF is spread across mini, base, and pro, instead of picking one hard action. The code shows how to call VW.predict, inspect the printed route and initial prob, and confirm the router is live before any LLM telemetry has been sent. This sets the face of the system, so later updates change behavior rather than toggling hard rules. Now we need to turn a single LLM result into the cost signal VW expects so the router can learn from what actually happened. This example turns one LLM routing outcome into the cost label Vowpal Wabbit expects. It maps a quality gate into numbers, so cheap answers that pass get a low cost, and failed answers jump to a high cost, like 25.0. The bandit label format is action, cost, probability before the feature namespace, and the action index is 1 based for Vowpal Wabbit. The code shows how to build that label and call VW.learn with the logged action, the observed cost, the logging probability, and the probbed features compactly. The printed output confirms the exact cost value that was fed back, which prevents cheap but bad routes from appearing successful. With single feedback, the router can learn, but it needs contrast across prompt types to specialize by context rather than global trends. This code gives Vowpal Wabbit enough contrasting feedback to stop treating every prompt shape the same. It creates a small batch of logged bandit examples that show mini is cheap on short, easy prompts, but expensive after a quality failure on a longer code prompt, while base is acceptable for that harder case. Each record is still bandit feedback, so VW.learn only sees the action that was actually tried and the probability that produced it. After training on that batch, the code calls VW-predict on a new code-heavy context and selects the highest probability model from the PMF. The printed chosen model and policy prob show the router beginning to prefer base for code-like prompts instead of following a stale global rule. Some traffic needs non-negotiable safety, We keep VW learning, but add a visible guardrail for sensitive prompts. This snippet keeps Vowpal Wabbit in the loop while adding a production safety constraint around it. VW Predict still provides the learned PMF, and the Bandit proposes an action. But the code then applies a simple floor rule for PII1 traffic. That guardrail raises the route to Pro by taking the larger action index whenever PII:1 is present, rather than burying the rule inside the model weights. The snippet prints whether the learned route was overridden and which safe model will actually handle the prompt. This pattern preserves adaptivity for most traffic, while making sensitive traffic explicitly deterministic and auditable. Finally, we want a monitoring number that is fair when exploration is active, so we add an IPS-adjusted cost estimate. This example ties the online Vowpal Wabbit router to an incident-friendly monitoring number. It computes IPS cost by weighting each observed cost by the inverse of the logging probability, which corrects for the fact that exploration changes which prompts saw which models. The snippet shows how to accumulate inverse propensity scores and divide by total weight to get an IPS-adjusted average cost for the routing policy. VW Predict still produces the online route for a fresh prompt, so decisioning and evaluation run side by side. The output includes the live online route and an IPS-adjusted cost estimate, giving a realistic baseline for routing plus monitoring. If you move this to production, map the prompt features and the quality gate to real telemetry. Log the chosen action and the VW probability alongside the pass-fail label for each call. Feed that stream into VW Online and compute IPS estimates in your monitoring pipeline, so alerts reflect policy changes rather than exploration noise. A quick recap. A Contextual Bandit router learns which model to pick per prompt from sparse pass-fail feedback, so the system trades cost against measured quality. Use it when you want that trade-off, and you can log pass-fail signals for each call. One caveat: logged Bandit feedback needs careful propensity recording, or evaluation will be biased. Next, tune the exploration rate epsilon and the failure cost threshold so the router finds cheaper models without increasing failure alerts. Increasing epsilon boosts exploration and speeds discovery at the cost of short-term spend, while lowering it makes the policy settle faster. If practical AI engineering helps, subscribe and watch the AI engineering videos.